Okay guys, so what I want to do in this video is very quickly run through some examples and concepts on electric fields and forces. Okay, so if you've gone through your first module, you've probably seen already most of this material. We just want to work it out a little bit in a simple context. So to start out, I want to talk to you guys about electric charge. All right, so everything we're going to be doing in these first lessons deals with electric charge. Just know that when we talk about forces that are created by charges or fields created by charges, all of these things are just the same as the forces that you guys have seen in mechanics. They move objects, they can accelerate objects depending on the mass of those objects, right? The only thing that makes these a little bit different is that we're adding in different types of charges, right? So when we had forces before, force is a force, it's mostly about magnitude, right? But here we have two different types of kind of force origins, right? One's being positive and one's being negative. So that's going to be the only difference. So what can happen here is that my force can be positive or negative, not depending on the direction that something pushes on something else, but whether these things satisfy a condition. Like for example, when I have opposite charges, they will attract each other, right? And if I have this same exact example, but I have two like charges, these charges will repel each other, but nothing else about this has changed. So this is pretty much the only thing that we're adding in here. Okay, and this idea is going to carry us through magnetism as well. We're just going to need a little bit of practice to make sure that we remember to apply this in our problems. Okay, so getting started quickly, we have electric field. So when I have some point charge, right? So let's say I have a charge here, and this can be at any coordinates. Let's say here we're going to make this the origin of our coordinate system. Okay, so it would be at 0, 0. We're kind of looking at this thing at 0, 0. I'm going to go ahead and put 0, 0 here. And this charge actually creates an electric field. Any point charge will create an electric field, right? So this is inherent in the fact that it is an electric charge. And the way we would measure what this electric field is, both of these formulas that I'm going to show you right now are extensions of electric fields. They're extensions of the same rules, right? Just one being, is this thing pushing against something, or are we just considering what it could do, right, compared to what's around it? So starting here, we have our point charge. This is our Q source, which I've written down here as our formula. Okay, so I have this, you'll see this K times Q source over R squared. So let's kind of see what each of these things mean. Our Q source is just our charge. This is our charge, and here it's actually how much charge. So this is, let's say, 4.2 coulombs. That's actually pretty big for our charge here, but let's say our charge was 4.2 coulombs, okay, coulomb being the unit we're going to use for these charges. Then this Q here, what you would put is 4.2, right, for this guy. Okay, next let's look at this R squared. What does this mean? So my field isn't constant, so there is, of course, field that is extending out in every direction, okay, from this charge, right? But you can think of this as sort of maybe like a light bulb. So a light bulb will do the same thing. It'll shine all around of it. As it shines, as it gets further and further and further away, the intensity of that light is decreasing, right? So this is a similar idea where the intensity of my field is decreasing the further away I get from my charge. So that's why we need this R squared. It drops off pretty quickly. R squared meaning every time we double our distance from the charge, we cut our electric field by a factor of 4, which is pretty huge. So remember this, that we're radiating this electric field. You can think of it in this way, kind of like light. And as it gets further away, it gets weaker and weaker in intensity. Okay, so this R squared here is just measuring for us, let's say from here to some point out here, okay, what is my radius? Okay, and remember, this might already look familiar to you from Physics 1, where you see I don't know what this is, but if I know my coordinates, right, I might know what the coordinates of this point are. Like, let's say this point right here might be 5, -5, right, for my coordinates. So in order for me to find R, I could do this. I just need to know my X and my Y, which I can do that by my coordinates, right? So I started at 0 and went to 5. So this right here should be 5. And I also started at 0 and went down to -5 right here. So this one should be -5. So if I made my triangle, I'm going to kind of make it here on the side. And I'm only going to put my lengths here. I'm not going to put the negative. This just means downward. Okay. Then I could find what my hypotenuse of my triangle is here. This is my radius. This is the distance between my origin point and my final point, using this kind of triangle right here. So we're still going to be using these right triangles a lot that you guys have probably used a lot in Physics 1. So don't forget these, okay? So in this case here, what we would do is, remember, this would be, we're using a squared plus b squared. The square root of that is c, right? So for this would just be 5 squared plus 5 squared, and we take the square root of this to give us my R, we'll call it, right? And the last part of this formula here is my K. So for K, what we want to do is we want to have our constant, okay? So you might see this in your textbooks or in your modules as something a little bit different. Here I'll go ahead and write what my K is, but it's 1 over 4 pi epsilon naught. Okay, and my epsilon naught is equal to 8.85 times 10 to the minus 12, and I think it's coulomb squared per Newton meter squared. So this value right here is, you can see 4 is a constant, pi is a constant, epsilon naught is a constant, this thing is a constant as well. So for us to, we can condense this whole thing instead of having to calculate it every time into just one constant K for us to use. So what we're going to do is we're going to do that, and we're going to use this as 8.98 8.98 times 10 to the 9. Okay? And then now this will be Newton meters squared per coulomb squared. So we have this here as 8.98, and then to make this even easier for us to always kind of remember, I find that it's really useful to just remember this as 9 times 10 to the 9. Okay? Because that makes it very simple to remember. Like, okay, I see this K in here, it's always 9 times 10 to the 9. So you can kind of round it, and your problems will still be pretty close. The last thing I want to do here is talk to you guys about force on a charge, right? So both of these formulas are very closely related to each other. You can see this right now. But what we have here is essentially, in order to know how much force, if I put a charge out here, okay, I know the field, how much force would there be on this charge due to this charge here in the origin? All we need to do is multiply this electric field times the Q of our target. Okay, I'm going to call this Q2. So we have the Q of our source. We know what this is, and we know the radius. Then all we need to do is multiply that by my new Q in order to get the force on that charge. So I can go ahead and write this all out. And you'll see it looks very similar to our electric field formula, except now I have another Q in here. Okay, but there's one more rule in here I want you guys to remember, and that is that for every action, there's equal and opposite reaction. You guys remember this. So if this charge at the origin is pushing on a charge that's out here with, let's say, 1 Newton, okay? So 1 Newton is what's being applied out here. Then it has to be the same as my Q2 is applying a 1 Newton force to this charge here at the origin. It's the force between them. Whatever force one is applying to the other, it's equal. It's equal in the opposite direction. Okay? So you'll use this formula right here as an extension, right, of my electric field, or you'll use your electric field formula as kind of a distillation of my force here. But either way, both of these things are going to be used frequently together in these first modules. Okay? And I guess we have a little bit of time, so what I want to do is go through an example with you guys with 3-point charges. Okay? So we have 3-point charges here, and I've placed them at different coordinates. So my Q1 I've placed at 0, 1. My Q2 I've placed at 1, 0. And then my Q3 placed at 1, 1. So the reason why I did this is it's actually very easy because if I look at this, okay, my R between 1 and 3, this is just equal to 1 because, you know, I'm going just here from 0, 1 to 1, 1. And then same thing here, oops, my R between 2 and 3 is also equal to 1. So I've done this so that the math comes out pretty easy. But what I'm going to do is just say, okay, from these two charges, what is the force that is going to be applied on Q3, right? The total magnitude of this force. So what we're going to do is we just use our force formula here. We'll use it twice. Okay. In the first case, Q1 will be my source and Q3 will be my target. In the second case, Q2 will be my source, Q3 will be my target. And this is the same thing as if two people apply a force on one object. What's the net force? We're doing the same exact thing. So don't think that anything weird is going on just because we're talking about charges now. You guys already know how to do this. So what we'll do is let's go ahead and say, I'm going to call this force 1, 3 because it's between Q1 and Q3. This is equal to K, and we're going to have Q1 is 1 coulomb, Q3 is 3 coulombs, and my R is 1, so it's going to be 1 squared. Okay, so I'm just going to put this as 3K. I'm going to leave K as K for now, right? So this is the force between these two. I also forgot here, just to make this easy, all of these are positive, but remember that if I change one of them to negative, all this means is that one of them is pulling instead of pushing. But for now, I just want to keep this all as pushing forces, okay? And then, so this pushing force, 3K, is actually trying to push away. Q1 is trying to push Q3 away with some magnitude of 3K. Okay, so I can draw it just for now like this, 3K. This is my force between 1 and 3. Okay, now we can do the same thing between 2 and 3. And it's going to be the K, and it's actually going to look very similar because we have 2 coulombs for Q2, 3 coulombs for Q3, and also a radius of 1 between them. Remember this radius right here, don't forget this is 1. So this here is going to be 6k. Okay, but what's the direction that we're pushing in here? These are both positive, right? So don't forget, these are both positive. These are all positive. So these two guys don't want to be together. So what's happening here is Q2 is pushing Q3 away. Okay? So we're pushing Q3 away. I'll call this F23 here. And this magnitude here is 6K. Okay? So what we have here there are two forces on my charge. So what's the net force here? What's the total force that is going on here? All we have to do is make a triangle. Same way we would for any net force of two forces. We make a triangle. So we have here, or you know what, I'm going to even just leave off a little arrowhead here. So this one would be, I'm going to call this F13, F23. This is 3K, this is 6K. And to make sure we don't forget, let's use a different color here. This is my net force. F net equals what? So this is what we're trying to find, right? So what you guys have to do is same thing we did before. Remember, this is a right triangle. So in order to find F net, all I need to do is square root of F13 squared plus F23 squared. You square root them. In this case, it would be 3 times 9 times 10 to the 9 squared plus 6 times 9 times 10 to the 9 squared, and square root that, and that will give you the magnitude here of my net force. Okay, and remember that we could also, if we wanted to here, we could also get this angle. What is this angle? We just have to use our trigonometry. So in this case, we would use something like tangent theta is equal to my opposite over adjacent here, or we can say here F23 over F13, right? And then we need to solve, of course, for theta by taking tangent to the other side. So it would actually be tangent inverse of these two would give me my theta. All right, guys.